All right, now I'd like to look at how this solution for the Schrödinger equation that works for the hydrogen atom could be extrapolated to the rest of the elements on the periodic table. And this is also an explanation for why we don't get the right answer using the Bohr model when we look at larger atoms than hydrogen. Okay, now there's always some confusion that goes along with how do we make this transition from the hydrogen atom to multi-electron atoms. And so what I want to start out with is just simply hydrogen. Okay, now here we have a single proton in the center and a single electron circling around. And so essentially then what we don't need to worry about are the interactions between this electron and other electrons, because there's just one electron in the hydrogen atom, and so that one electron can go into all of these other different energy states. And so it's because that one electron doesn't have to interact with the other electrons that we have something that gives us the same answer with the Bohr model as what we get from solving the Schrödinger equation. But if we go to heavier atoms, where Z equals the proton number in the nucleus, this is the only thing that's going to change the electric potential that is associated with a single electron going around a multi-proton atom. Then this is a single electron energy, meaning that there are no other electrons in this multi-proton atom. Then En would be equal to Z squared times 13.6 eV over N squared, where Z again is our proton number. So in other words, if we had helium here, and that would also have two neutrons, but the neutrons wouldn't have anything to do with the electric potential, then we would expect an energy state of energies to go up by a factor of 4. But it's not quite that simple, because how do you get just a single electron orbiting around a multi-proton atom without other electrons coming in? And so this creates such a problem that it essentially cannot be measured. This is a theoretical value, but it can't be measured because other electrons are going to naturally want to come in, unless you have an extremely energetic state, like what might happen in the center of a galaxy when you have particles spiraling in toward a galactic-sized black hole. You get huge amounts of ionization energy. It might be possible to tear off all the rest of the electrons and just leave one behind. But you would need so much energy that you'd probably change the state of the matter before that would happen. And so essentially then it's impossible to actually have a single electron orbiting around a larger atom. And so what we need to do, instead of looking at this expression, is to look at, we give up on just having a single electron, and so we have to look at an expression for multi-electron atoms. And what that looks like then is En equals Z effective squared times, and this should have a minus out in front of it, times 13.6 eV over N squared. Where Z effective is the effective proton number of the nucleus. So we might wonder then, well, what if Z is 10? Then what would Z effective be? And why would it be different than 10? And the answer is because of what we learned in Physics 208b about shielding. So let's say that you're in an n equals 2 state here. You're an electron in an n equals 2 state. But because you can't stop them, you also have electrons that are filling up the n equals 1 state. And maybe there are 3 protons in this nucleus. Okay? And so with 3 protons, then that might be, we can see up there, that would be lithium. Okay? And so for this, then, we see that there is essentially a shell of electrons that are in closer that can cancel out. So this is minus 2q. This is plus 3q. So out here, using Gauss's law, the net charge enclosed is just going to be equal to 1q, not 3q. Okay? But it's not quite that simple because the electron probability actually does extend out farther for these electrons than the orbital radius of this other electron. And so this electron isn't completely shielded by these 2 electrons from the 2 protons in the center. And so this Z effective then is something that is more easily measured experimentally and then popped into the equation in order to give us an effective proton number in the nucleus, which can then allow us to adjust the values for En. But the Z effective is now dependent on some of the solutions to the Schrodinger equation. And so this is the reason why the energy levels get shifted and the Bohr atom is no longer the way to go with heavier atoms in order to get an expression for the energy level. Okay? And so with that idea in mind, we can look at some of the properties of elements on the periodic table as a function of their n value. And so here, for n equals 1, we see that the ionization energy goes up within a given n value. And then here's for n equals 2. The ionization energy goes up for n equals 2 within a given n value. So this is a given n value, but the ionization energy is getting larger. Why? Well, if we go back to our periodic table, here we see that for n equals 2, you have more protons in the nucleus, but you're basically at the same distance away from the nucleus. Okay? And so ionization energy then goes up for a given n value. And so the reasoning then, why this is true, remember ionization energy is just the energy that is required to remove the electron to infinity. And so why does the ionization energy go up for a given n value? The reasoning is that the electrons are a similar distance from the nucleus, but with a larger number of protons. So that means it's harder to tear the electron off because there's more protons pulling in on it to keep it from escaping. So if we look at this expression here, we see that Z effective isn't going to be too much different for any of the electrons that are, say, in this orbit, because they're going to feel essentially the same amount of shielding as they experienced before, but we're going to get, for larger and larger atoms, more and more protons in here that are going to be anchoring these electrons in more securely. And so therefore, the ionization energy goes up for a given n value, because there's more protons in the nucleus, to prevent those outermost electrons from escaping. And so we can see then that this is also true for n equals 2. Now for n equals 3, we see the same pattern. But when we get to n equals 4, we get that pattern is messed up a little bit by the fact that for n equals 4, we get some 3p orbits in here before we get to the 3d orbits. Okay, and so after we get past here's n equals 1, the ionization energy goes up from hydrogen to helium. Here's n equals 2, ionization goes up from lithium to neon. And we also notice that it's hardest to ionize a noble gas. Okay, because the noble gas not only has a filled subshell, but it has the maximum number of protons to hold that the last electron in place, and so therefore it has very little combining power from a chemical point of view with other atoms. And then things get a little more complicated for larger values of the atomic number. Another thing that changes is atomic radius. Now atomic radius, you might think that for a bigger atom you would get a larger size. But no. Within a given n value, the size gets smaller because there's more protons squeezing down on those electrons, pulling them in tighter. Now this isn't a big change, but it's noticeable. So notice here, previously I said that electrons are a similar distance away, but not quite the same. The atomic radius goes down, so actually as you add more and more protons, the size of the atom for a given n value gets less. And so the atom takes up less space than it does when there are fewer electrons in the outermost shell that corresponds to a given n value. Okay. And another thing that we can say is that the filling order follows essentially the order in which the elements appear in numerical progression on the periodic table. And so we first go from 1s to 2s, then to 2p, then to 3s, 3p. But before we can get to 3d, the 4s comes in before that. Okay, and so why is that true? Well, the 3d spends more time farther away from the nucleus. And so therefore it's at a lower energy, even though, because there's more shielding essentially. The 3d has more angular momentum, is thrown out farther away from the nucleus, and so therefore spends an average amount of time farther away from the nucleus than the 4s does. And so that puts it essentially at a higher state of energy. That's more potential energy, more distance away from the nucleus. Then we go to 4p, but then 5s before we get to 4d, and then we have 5p, 6s, and so things start getting a little bit more complicated as we get to higher and higher energy states. But if we go back to the periodic table, we see here, this is 3s, this is 3p, so everything's going fine. We have 4s, but now we have 3d. Okay, so 3D comes in, and all 10 of these come in before the 4p comes in. And then we have our 5s, but then we have our 4d here. And then we have our 5p orbits in here. That's these 6 are the p orbits. These in the middle here are the d orbits. And then eventually, when we get to 57, we splice in the f orbits. Notice we have 10 of the f orbits, so that corresponds to m sub l equals -5, -4, -3, 2, 1, 0, then +1, 2, 3, 4. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14. So here, D, that corresponds to L equals 2. So this is L equals 3. Okay, so this, I'm sorry, this goes from -3, -2, -1, 0, +1, +2, +3. That gets us to 7. But then we have a doubling of that because of the spin. Another thing to keep in mind is, as we're looking at the splitting of these, it always starts from lower m sub l. So let's say that we were to look at some 2p orbits here. Okay, and so these 2p orbits, this would be for boron, carbon, nitrogen, oxygen, and fluorine, 1, 2, 3, 4, 5, and then neon. Okay, so this is going to come in with m sub l equals -1 first. Then, and the spin would be down. Then we'd have m sub l equals 0 with a spin down. And then m sub l equals +1 with a spin down, like this. Okay, and then we go to spin up. So we have a spin down, but then we have a spin up with m sub l equals -1, m sub l equals 0, and m sub l equals +1. So the question then is, why do these fill in terms of their m sub l values if you can only tell what the m sub l value is by projecting a magnetic field into that region of space? You'd think that the filling order of these electrons would be independent of the m sub l value. But no, it's not, because of the effect that the spin and the orbital angular momentum have on each other. And so each one can exert a magnetic field on the other one. And so internally, you can get internally generated magnetic fields in which these magnetic moments can interact with those internally generated magnetic fields. And this allows for a difference in the filling order. And so we start out then with the lower value for m sub l, then the 0 value, then the larger value. Then if this were, say, instead of being a p orbit, if this were a d orbit, then you'd have 10 of these, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this would be m sub l equals -2, spin down, m sub l equals -1, spin down, m sub l equals 0, spin down, then m sub l equals +1, this would be -2, -1, 0, this would be +1, okay, and so that would correspond to this, and then m sub l would equal +2. So the -2 one already came in, then the +2 one comes in, and then we, 1, 2, 3, 4, I'm sorry, this comes in like that. Okay, so all of these have come in. Okay, so now we repeat it again. M sub L equals minus 2. Now this will be down, this will be up. M sub L equals minus 1, down, up. So that's just, it's the same thing that I did here, but with one more value for M sub L. M sub L equals 0, so that would be this one. But now we have an electron that comes in with the same orbital momentum state, but with a different spin state. And so then we'd have M sub L equals plus 1, down and up, and then M sub L equals plus 2, down, up. Okay, so that's our filling order in terms of first M sub L value with spin down having the lowest energy, and then filling back in with spin up as we get farther along in our d orbits. So this is 10 d orbits. We have 6 p orbits. And so this is, roughly speaking then, the filling order for the elements on the periodic table. Now if we go back up and we look at a d orbit here, what we see is that element number 26 is iron. That's 1, 2, 3, 4, 5, 6 along. And so here, if we come back down, we see how this corresponds to here. 1, 2, 3, 4, 5, 6. Okay? So what we see then is for iron, we have a whole bunch of spin down electrons that contribute to the magnetic properties of iron. Okay? And you would think that maybe the element before iron would be even more magnetic, that each atom has its own characteristic internal qualities that make this just an indicator of how magnetic a substance would be. So it turns out that the ferromagnetism of iron is related more to the electron spin than it is to the orbital angular momentum. And when you get a bunch of unpaired electron spins that are all pointed in the same direction, this then allows for the domains to form and for iron to become ferromagnetic.